Question 19. A toy car travels around a racetrack. After one lap, it's back at the start position. So it does something like this. There we go, start and end. Explain why the velocity of the toy car is different from its speed as it travels around the track. So velocity and speed are the things we're comparing here. There's loads of things we can say here, so I'll just give some examples. Velocity is a vector, and therefore speed is scalar. Alternatively, you can say that velocity is speed in a certain direction. Speed doesn't take this into account, doesn't consider this. There we go. What else can we say? Speed is distance over time, whereas velocity is displacement over time, because displacement is distance in a particular direction. And lastly, something else we could say, the displacement considers start and end point of car. So our displacement would be the straight line distance from the start to the end, whereas distance is only concerned with how far our car has travelled or over what distance our wheels have rolled. So if I were to draw a similar track, probably not to scale, but let's say that car A has travelled the same distance as car B, but it's clearly had a displacement because there's the start and there's the end, and there's a straight line distance between them, whereas car B might have travelled the same distance, it's covered the same amount of ground, but it's ended up back here, so its displacement is 0 because it's ended up back where it started. So for this question we just needed 2 points. I think any of these points I've made, so this one and that one, or this one here, or velocity is displacement with time, and then things like that. Just so long as we're making it abundantly clear we know the difference between velocity and speed. Question 19b, part 1. The mass of the toy car is 5 kilograms and it has an acceleration of 4 meters per second squared. Calculate the force needed to accelerate the toy car. We've got our equation here. So let's have a look at our ingredients. 5 kilograms, that's our mass. 5 kilograms. That's a standard unit, don't need to convert anything. Acceleration equals 4 meters a second squared. That's another standard unit, we don't need to convert that. Got this equation here, so force equals mass times acceleration equals mass 5 times acceleration 4. I'm feeling lazy, or rather I'm feeling efficient. I'll use my calculator, 20 newtons, so 20 newtons down here for our answer. Question 19b, part 2, suggests why the actual force needed would be more than this. So now we're applying physics, but in real life. In real life, a car would be rolling along the surface or the road or whatever. It'll encounter some friction or air resistance as it's going through that. So we'd actually need to have a greater force than that. This force would be for our car where there's no friction or no slowing forces at all. So let's just suggest that. So the car would be subject to drag forces. There we go. Drag kind of encapsulates friction and air resistance and all that. So making it clear that not all of the energy that we're trying to put in is actually making it to the car. If anything, that's probably another way of saying it. We could say that the energy transferred to the car isn't going into just the motion of the car. It would be dissipated. But this is why. It's because there's some drag forces there that we need to consider. Question 19c, part 1. Another toy car requires a constant force of 30 newtons to move it along a surface. Calculate the work done on a car when it moves a distance of 50 meters. Got a helpful equation again. Let's just identify what we've got. Force equals 30 newtons. That's a standard unit. No need to convert. Distance equals 50 meters. Another standard unit, no need to convert. Happy days. So work done equals force times distance equals 30 times 50, 1500. They've given us our unit for joules there. That's handy. So 1500 joules. Seems quite a lot. Question 19c, part 2. Calculate the power output of this toy car if the work is done over 75 seconds. Use your answer from this. Don't mind if I do. Power output. Power is work done over time, or just energy over time. So let's see what ingredients we've got to do. Oh, we've got some seconds there. So time equals 75 seconds. Seconds is a standard unit, no need to convert. Energy or work done. Energy equals what I used here, 1500 joules. Don't need to convert that, it's a standard unit. So power equals energy over time, 1500 divided by 75, 20 watts. There we go.